Section 6.3, vertical stretches and compressions. In this section, we're going to look at what happens if we stretch the graph vertically or we compress the graph vertically. It's a rather short section, and so it won't take us a whole lot of time. You'll notice the notes are rather short for this one. So let's define first what we're talking about when we say a vertical stretch or compression. So a vertical stretch or vertical stretching is the stretching of the graph away from the x-axis. And a vertical compression is going to be the squeezing of the graph toward the x-axis. So when we talk about that, let's kind of explain what we mean. So if we know a function f at x, and we create the function g at x is a constant times f at x, that's when we have a vertical stretch or compression. The best way to illustrate this is to take a look at how this affects a function we're familiar with. And so let's go back to our function f at x is x squared. So like I did in an earlier section, I'm going to first graph f at x is x squared, your standard everyday general parabola. I put some points on a table so we'll be able to see what happens with the table. And there's my function. Now what I'd like to take a look at, though, is g at x is 3x squared. And so if I take a look at 3x squared, and I look at the graph, and I actually on this one put the original x squared and the 3x squared on the same graph, what you'll notice is the shape is the same, but it's almost as if I took the two tails of the parabola and just moved them straight up. That if I grabbed onto it and just moved it straight up. Notice the effect that it has, if I look at the table, is it has no effect whatsoever on the x's. Really, the x's are not affected at all here. But what it did was it took each of the y's and it multiplied it by 3. And this makes sense to us because notice the 3 is out in front of the original x squared. So that appears to me to look like an outside change. And remember, outside changes affect the y's. So when I do these vertical stretches, and we'll notice when I do the vertical compressions, that the x's are all going to stay the same, and the stretch or the compression is going to take effect on the y's. So notice in this particular case that my points a, b, my original points in my original table, became a, I kept all the x's the same, but 3b, I actually multiplied each of the y's by 3. Let's take a look at the compression situation. So now I'd like to graph g at x is 0.5x squared. So again, I graphed both of them and I made the table, and once again I noticed the same type of thing. All of my x's I could actually keep the same. It's an outside change. And what it did was it took each of the y's and cut them in half. And so notice when I look at the graph is closer to the x-axis than the original x squared graph was. And notice the point AB, once again, keeps the x value the same, but actually takes the y value and multiplies it by 0.5. So in general, if f is a function and k is a constant, then the graph of y equals k times f at x is the graph of y equals f at x either vertically stretched, if that constant's bigger than 1, and compressed if k is between 0 and 1. Notice I didn't talk about negatives here because then we have that issue of reflecting over the x-axis. So I get stretched in the one situation when the k is bigger than 1, compressed when the k is less than 1. So let's take a look at a set of tables here, and we'll kind of go on and just do this example rather quickly. So given the table below, so I have 1, 2, 3, 4, 5, 6, 7 as my x's, and 3, 2, 1, 0, 1, 2, 3 as my y's. So now, suppose I wanted to do f at x, I probably should be g at x, but f at x is negative 4 times f at x. Like I said, I probably should change that, make it a different function. What's going to happen is the point AB is going to go to being the point A negative 4b, because it's going to take the old y values and multiply them by negative 4. And you'll notice that's what I did to make the table. I kept the x's the same, multiplied by negative 4 on the y's. Now let's take a look at a slightly more complex one. And this one, our new function, and again, I should probably call it g at x, is 0.5 f at x plus 3. And so now I have two things going on. I've got that vertical stretch, or vertical compression actually in this case, and a shift up. And again, just like following my order of operations before, I have to do that here. And so what's going to happen is I'm first going to multiply the y by 0.5, and then again I have a second change, and that's a plus 3. So then I add 3. So I have two choices. I could add 3 and multiply by 0.5, or multiply by 0.5 and add 3. Using the order of operations, the correct way is to multiply the y by 0.5 and then add the 3. And so my point AB is going to go to the point 0.5b plus 3. The A is going to stay the same though. And so I did that with the table. Check out the numbers, kind of do the math out, convince yourself this works. We're not going to study horizontal stretches or compressions at this time. We'll actually talk about them a little bit when we talk about some trigonometric graphs, but right now I'm going to leave those off and wait until we talk about the trigonometric graphs. Well, that's all there is to this section, so now you can go on and take a look at the problems from the book, do some practice, reread this, and we'll again talk about this in class.